Welcome to this module on a more detailed architectural view to the calculus. And you want to concentrate on numbers and expressions on the one side and on characters and lists on the other side. So we had a certain vocabulary we developed for our profession, and we want to use this vocabulary to look at computing and what coding is about. So, and I think that these symmetries are very important for our specific access to computing. So let's have a recap and to have a proper start. Again, this triangle. This had been the memory of the last day. These are the dreams of the last night. Ichnographia and Scenographia are the talks of today. So, today we are in a quantum space. These are characters of the scale. We call that the scale of life. And we are looking at the last day. These are characters of the second scale of, that's the scale of time. With here, in the 3 5 9s, we are looking at the complex number space. So we said, and these are the numbers, and these are the characters. So the numbers play at night, the characters play at day, and we have two different kinds of characters. So the characters of today are, we said, this is coding. The technical characters of this is coding. The technical here is a perspective drawing, as it had been the phonetic writing in space chair 1. That's a phonetic writing there with the antique with T. Good. Now let's go for the numbers. So for the dreams of the last nights. And the interesting there is that the onlyest order to get, the source of order you can get is, there are the prime numbers. And the prime numbers are of absolute disorder. So that's a strange setup. And we had this problem with the circle and the branching and the infinity, that you can't meet the circle. This is the story told in another way with the arithmetic. And now let's look how this can be illustrated with the code of today. So we can have, for example, in Mathematica, we have a prime. This is the 10th prime number, or this is the 100th prime number, or this is the 100,000th prime number. So if we put there a range, then we get a list of 100 and get the list of 100 primes. So these are the first 100 primes. And the characteristic is that you can't, there is no regularity in this. So for example, you take all the distances, or the distances to the distances, whatever, or you get some proportion. There is no proportionality, there is no order in that. So which means if you want to go for the next prime number, 100 and prime from 101, you have to go with this number and test whether there are factors, other primes, which can be multiplied to get this number. And you have to test all of them until you're sure. That's the problem. So there's no prediction with prime numbers in time. So therefore it's something like the prime numbers are kind of the body of the night. So, or the medium of the night. So to illustrate that, this is a small program using the first 5,000 prime numbers. The prime number 5000 is 48,600. So we take this last 4600, make a table of ones. So it's a line of 48,000 ones. This is data. And then we punch a 0 at the position of a prime numbers into this black, so 0 is white, and into this black line. So therefore we get, at the position of the prime numbers, we get zeros in a line of ones. And we partition that and make that in chunks of 300 to get an array and show this array as an image. So this is the absolute chaos of primes. That's the only source to make sense at night. So this is in strict difference to white noise, which is a source of communication. This is a source of all reason, and this is a source of all communication. This is in time. So it's a background of, in space. This is the background of any activity in space. So we do again the same number, make randoms, O's and ones, partition that into 300 and make an image, and that's white noise. So this is not chaos. So this is a background of space. This is a body of time. Good. What is arithmetics and what are numbers about? And then we can talk about scales of numbers. So we will need this one. I wrote this function, delivered it. You can find it with the supporting functions. You have to evaluate that first, if this is blue. So this shows the sequence of fractions. So this is how to branch on the area as we've shown. You can put that in a circle. Now we put it on the line. So this is a unity. This is a division in 2, and this is in 3. So we can go for 12. And then you see how within 12 steps in time we can subdivide a unity. So that's fine. The interesting thing is this here. Now we project these points of cutting, of partition, the partition points, and project that to the line. And you see there's no regularity in that. So you can't make simple steps in space. You always have to say, yeah. So if you go, for example, for 424, you see there are certain spaces it's very hard to get to, certain positions, and it's not continuous. So, or we have the golden ratio. So this is the number with 100, this irrational number like all the others, but this is the number which is the worst number to get to. So it's somewhere like this one here, and somewhere here which is the most distant to all the other numbers. If there are infinite amount of numbers, this number has the biggest difference to all the other numbers. So this is the worst number to get to. That's the golden ratio. This is 1000, so I always like these things. Nothing to predict, but you need an algorithm for do that. We will see what an algorithm is later on in the complex numbers plane. So we have this, and then, for example, this is to put this number into a graphics. This is what we like with them. So it's just this number is rotating around the center point, increasing the number of the golden ratio and radius, and then you get these patterns. So you see the radius, cosinus, sinus, and they all the golden ratio, and you make 1000 points. make that as a graphic. So this is what we like. So, but arithmetics is interesting. So, and so this is in all scales of space and numbers, it's the same. So now let's go. What arithmetic is about. For example, the scale of things. So this is how in Babylon and Egypt it worked. So we have, even if it is complicated, we simply say 2 plus 3, 2 plus 5, and it's always the same procedure. So this is what the abacus is doing. It's making it accessible, making straight steps in time in calculation. So very simple rules, a certain routine to make straight steps in time. So which is always a prediction. So calculation is always a prediction. So that's in here. Going to the next scale. These are the rational numbers. This is with a scale of space, and this is antique Greek and Rome in our culture. So here now you get two of these numbers into proportion, and you are able to make arithmetic with this. And Mathematica is able to do this arithmetics. You can, for example, go here and simply calculate. You can make it here. You can make here. You can make this, and so on. These are the rationals. So it's again very simple to do, but look behind the scene. For example, here, these are the first 20 numbers, like a calendar. So it's the first 20 numbers. Grid, make a grid by 5 and show partition by 5 and show it as a grid. So have it here. So we can have 40. So and now go and show for the fraction integer. So these are the prime numbers. How to go to these points? So if you are at, if you start and you want to go for 34, then you have to multiply 2 by 17, or 5 by 7, or 3 by 13, 2 by 2 by 2 by 5. So you see, there's no regular scheme how to do that. But with our calculation and writing, and this number system, the scale of the rational numbers, it's simple to do. Yeah? Make clear, simple predictions in time. So, and this is how it looked like. So if you're able to do these kind of calculation, this is how it looked like with the eye of the time, of the space. So we have this Euclidean, with the eye of time. So we have this Euclidean geometry. This is how things work in antique to get stability. You don't have to, so I think there's no way to understand that. It's important that you see these phenomena, and you understand that now this is with the numbers, this is with the symbols. So you see the problemicity of it, and then you see the numbers of that day. Now you need see the characters of today. These are the characters with the eyes of time, the characters of that time. So they had phonetic writing about that, sentences like what we are able to do here and with our writing. Euclid never made drawings in his geometry, or very few, if any. So, next step. Now we go to Renaissance. This is what we call, today we call the real numbers. And in computing, these are computable numbers. So we can do these kind of things, like we do with any calculator. Huh? It just works. These are the real numbers. If we are using these numbers, we are in time, in the scale of time. This is chair 2. This is what we called chair 1, the rational numbers. So in the scale of the rational numbers, lines don't cut circles. In the scale of real numbers, they do, because they deal with infinity. Now I show, so I can show you how this works. This is behind the scheme of the real numbers. So what we have is we introduce a variable. So it's any kind of number which meets a certain criteria. So this criteria is that we say 1 plus x. So we have multiple proportions. So this thing, x, whatever it is calibrated to multiple other agents. So these can be rational numbers. So and if you do that, this is an A. Now you can say expand A, and these are these so-called polynomials. So we can ask a polynomial, what is if there is a time number A, x, if x is, for example, 1, then you say, you answered with this. Then you can say this, then it's answering with that. And you can say plot A, x from minus 10 to 10, and this is how it normally looks like. This is what we know at the drawings, and this is what we work with, the differential and the curved lines and so on. It looks like this. This, our perspective drawing, is a difference between 2 points, and by that you get always a curvature as a line. So these are the numbers. This is a complication, so you see rational here, and you see the ordinal numbers here, and the cardinal numbers in front. So it's again a combination, like we have the combination here, duck to this, and this to this. We have a series of these and these. So don't try to understand that. It's important that you get these phenomena. So this is another scale, numbers getting more nested, how to deal with the primes. But with these strategies, we can go further. And these are the curves of Newton, of Descartes, of Leonardo, of Alberti, and so on, with today's eyes. And this is with today's writings. Good. Go for the complex. Here. Yeah, this is how it looks like. And now complex numbers, and they look like this. You have any kind of number, and again you have a pair. You have a real part, which is of this kind, and you have an imaginary part, which is again gets an a scale. You can do arithmetic with it, and then something's coming out. So, don't want to discuss this too much, but two things. First is this how it looks like. So, for example, go here. As we had a plot here, x minus 1 to 1, z minus 2 2i to the 2 plus 2i, so it's on minus 2 with plus 2, but in 2 dimensions, in the real and the imaginary. And then make z square plus 1 to z square minus 1. And go here. This is a typical thing of a curved space. So here the lines are curved, and I would say this is with Newton. And if this is the light of, the optics is with lines of light, these are the colors of light, because you give the light a quality. So there's a parameter, so red, green, and so this is a color. And then over time they changed color. And this is the image of light today. So, and it's not the line which is curved, it's a space which is curved. It's not that space, it's so this is always, yeah, like here. So this is always time and space. And here again, it's time and space, so it's space-time curved. And this is the same here, space-time curved of the other one. So this is what we said here. This here is in a certain proportion, and you are able to deal with that. So it's always space-time if you go for coordinates. And here again. So, but these are the typical representations of today. If you, to get an idea what is behind, I can't explain it. So this, for example, is, go for this. These are the typical, so this is a certain line. So you see it's a polynomial, but we can put this polynomial, that's the interesting thing. To escape. And then this is a sinus function. So if you put the sinus function is, you see, it's simply, it's minus, plus, and so on. It's a polynomial, but infinite. And then it's sinus. And we are used to these things, so it's the Taylor sequence of that. So, or you go with this one. Again, this is infinite. Oops. Go here and say, for example, 3. Then you have this kind of series. How this develops. If you go to infinity, then you get the square root of 1 plus x. If you put that x to, for example, so it's 1 square root of 2, this is x is 1. So then you see square root of, this is square root of 2. If you put that to the real number space, then you get the square root of 2. So these are the algorithm. So this is how computers do and work towards infinity. So work in time to go better and better precision in the complex number space. No, in the real number space is how they work to constitute the writings in the complex number space. So I think this is enough for the numbers and how it looks like. So for the eyes, for the writings, and they get an idea of the different scales. So complete different is with characters. We said that the numbers are so the numbers are correct but incomplete, minus, plus, and they are complete, not correct with the characters. So now we've seen that about the completeness of the numbers and the struggle around with arithmetics. This is what we had called the dreams of the night. And with the characters is geometry. And we said just with an alphabet of 24 characters, you say R, N, T. And there's an out. You can get anything, but it's never correct. This is what we said. Or we can say RT and then here an abstract concept. You can do anything and here everything. So to make it, for example, with the eyes, this, for example, is the memory of the last day, and this is how to look at it. So this is with a prism of Newton. So the idea is to make the color of light in the scale of time. So, and this is Goethe. So this is a slit in a dark chamber. So this is a spectrum. It's a piece of glass in the bright light. This is a slit in a dark box, and then you get another spectrum. So that's interesting. So now with our image of the atmosphere or the environmental or the scale of understanding of our space today is of image. So therefore we currently do what we do with code. We put this here, the Newton Newton-like spectrum. This is RGB and this is orthogonal. So this is of space, so this is of the last day. So if we go for the, this is a physical space. And that's interesting here. This is HSB. This is a color space which is physiological. And that's at night. This is with Goethe. And we have circulation there to get the color, brightness, and saturation. So I think these, so both of these things here, these are with the lines of light. So these are experiments on level 2, on the real number space. This now is with our understanding that the volume of a space is of image, not on a spectral color. It's moving over time. And now we project, with these eyes, we project it into our operatable number spaces, RGB, HSB, physical, physiological, Goethe, and Newton. It's very interesting. It works pretty well. So, let's go to the next step. These are numbers and characters. Let's go for the details of the characters and how to operate on them. For example, this here is a text. So, and then we can say, ask for a string length, for example, of this text. It's 24 characters long. So, or we can say string take. And we want to have the first 6 characters. Or we just want to have character number 6. So, or we want to have character 6 to 12. So, this is how to access it. We can go here and say B, assign to B. This is another line of text. And we can say C is string join of A, B. Then we have this. Or inverse is string split of C at the position at the point, and then we have the 2 text, and we will see that it's a list, and we can get the first sentence and the second sentence. So I think this is with text to get an idea, or you can do it with long text. For example, this is Hamlet. So, and now we do the same thing, yeah? We say string length of Hamlet, and it's 170,000, so we can say string take of 10,000 to 11,000. Ah, it's not A, it's Hamlet. So then you get a subtext. Or you can say string position, as we have it with A, and we can ask where are the eyes, and then they say it's 1, 2, 3 eyes. So now go for Hamlet. And ask for eyes, but we can, for example, call for duty. Then these are the positions of duty. Now we can say string take Hamlet, and now we make a variable because we want to have all of them. Make that a pure function and map this list to that, and this should deliver all duty. But now I can say plus minus 20 characters plus 20 characters. So this is the environment of this duty, and then you get all the environment of duty in this text. So very simple and straightforward. There's a lot of nice and good tutorials how to work on text and on strings. I think you get an idea of how this works, how we can work with today's writing on the writings of the last days. Good. Now go to lists and expressions in the next level, and then we are done, I think, for this overview. And the rest is go into semantical details. Do the same thing here. It's just another writing. So, for example, give that a name, symbolize that with a variable x, and assign it delayed. This is the delayed function here. It's just another writing. X plus 1. So when we symbolize this pure function as with add. So if we're doing this, then we can ask for information of add. It's a symbol and the definition and so on. I'll go for, yeah, that's the same. So if we use it, we can use it now as a symbol and address a certain number to it, and then it's calculating like that. If we want to make a mapping on it, go here and say all the list of A, and then it's doing the same. So this is expressions. So everything works like that, as we had with the forwarding of the images. So image is a symbolized function like this, and then you put in here an array of 9 numbers, and then you get an image of it, instead of an addition, whatever you like. You can ask what is this image, and you get all the definitions and things, what you can do with it. Good. Or here there's a polyhedron data, there's a database of all, or it's an encyclopedia of all polyhedrons. And now we go for the dodecahedron, and we just go for the coordinates, and we show this. These are coordinates in space, which is a dodecahedron. So if we show that, then it's looking like that. Yeah. And you see it's always folding, and these expressions are either to manipulate, or to manipulate data and render it, or unfold it to data, or fold it back to a certain media, and so on, or manipulate it, or whatever. So all these expressions are just to rotate things. So it's a circular writing. So, and then here, for example, we had this sound of Apollo. Phone call.
With the White House, and this certainly has to be the most historic.
Okay, and if you want, if you get this, the audio data of that, then you get a list of numbers. Good. I think that's it. So we summarize. So we had the numbers and the characters, and here now we have the lists. On the next level, we have the lists and the expressions. So these 4, I think you can talk more about it, but I think they are enough to get the picture. So it's a lot of meditation and needed, and the rest is, I think, it's going into more practical and more application stuff. So we have the symbol, and then the symbol can be numbers or characters or lists or expressions, and we have these symmetries. To sum up, again with our triangle. So here are the numbers and the lists. Here are the characters and the expressions. And here is a symbolic writing code. So, to give it more substance or more color, so with this triangle, what is it about? So if we write in code about in characters and in expressions, that's tragedy. So this is satire. And this is comedy. So writing about with a new tongue, writing about the dreams of the old night, of the last night, that's satire. Writing with a new tongue, or talking with a new tongue about the last day, that's tragedy. Writing about today, it's comedy. Whatever it means. So, or If we go to food, we have the Cass. We have the Prosperity Burger. And we have molecular. That's it. Thank you. And the rest is in detail in our discussions. Of course, on the theoretical level, on the practical level, I think we go to the tutorials available, and we will see how to support that towards graphics and towards AI, cryptographics, to certain applications in this primer. Thanks for watching, and see you.